Okay, guess we can go ahead and start the class. Today we are going to finish chapter 2, and hopefully on Thursday we will start the discussion on chapter 3. Your homework will be posted on Thursday, homework 2, and you will have a week to submit your answers. Okay, homework 2. The homework will be based on the discussions we have had on chapter 2 of the book, and that's it. Is there any questions about the material from the previous lecture or homework or anything else? No. Okay, so there was one thing that I forgot to mention, one concept that I need to mention, and that's the center of pressure. Center of pressure. We talked about this concept. We actually saw the equation and formulas, but I forgot to mention the name of that point. So center of pressure is a point at which the resultant moments are gonna be 0. So what does it mean? Essentially means that let's go back to, if you go back to the hydrostatic forces on a wall, however they look like. The idea was we replace this distribution of forces, the pressure, with a resultant force that passed through a point, right? X of r and y of r. And we have the equations on how to find these points. That point, we were able to find that point by writing a moment balance. F(r)(y)r equals to the moment of pressure that is generated by pressure, right? That moment balance actually means that the moment at this point, the resultant moments at this point is going to be 0. So the point we found, that was the point that the resultant force passes through, is called the center of pressure. That's it. So you just have to make sure you know that, right? That is actually the point the resultant force passes through. Resultant force. So that was a topic that was a leftover material that we needed to talk about. But today's topic is about the rigid body motion of the fluid. What does it mean? It means that you have a container that contains some sort of fluid, a liquid most probably, and then you are moving the whole container all together. You have a lot of containers of fluid here. We want to analyze when you are moving this container like this. So it's a rigid body movement of this fluid. And this type of movement is going to be linear motion. This is the first thing we want to focus on and analyze. If you go back to the hydrostatic equation we found, it was a very general formula that gave us the changes of pressure in any direction minus gamma in k direction. This is due to the weight. Due to weight. And all of this has to be equal to rho multiplied by your acceleration. Okay, that was the general. Oh, there's a negative sign here as well. That was the general hydrostatic equation we found. And for a case of a fluid at rest, acceleration was 0, so the whole thing was going to be 0. This is an equation we have seen. This is an equation we found in the beginning of the class. And as you can see, because it involves vectors and the gradient itself is directional, we can actually write this equation in 3 dimensions. So partial p, partial x, the gradient of pressure, this is pressure. In the x direction is going to be equals to gamma k, but we only have gamma in the k direction, so this is not present in the gradient of x. Just write it down to make sure you are clear. Is going to be equals to rho a of x with a negative sign. We can write this for the other direction as well. Partial y, partial p, partial y is going to be equals to negative rho a y. Now for the z direction as well, we're gonna have az, but here the difference is that we are going to have gamma as well. Gamma is going to be your rho multiplied by the gravitational acceleration. We can combine these two and do g minus a of z. So we have had this equation. The only difference was that we set the acceleration to 0. When you are having motion, you don't set the acceleration to 0. That is the main difference. Okay, so let's try to further this analysis. This is the general equation. We are not talking about the motion in any specific direction. But let's say we are dealing with this container of fluid and it is moving in this general direction. Okay, your coordinate system looks like this. This is going to be your y direction. It's going to be your x, and this is going to be your z direction. How would the fluid look like when you start moving it? How would this free surface change? Just think about it. Is it going to move at all, or is it going to remain the same? And we are moving it in this direction. Of course, the free surface is going to change a little bit. It will tilt in this direction. So we will have some fluid movement in the z direction and in the y direction. You can conclude that based on the changes in free surface. And this is something we can understand, right? When you move I wish we had a see-through container, then you could see the free surface actually changes shape and it will become something like this, right? But I guess you can imagine it yourself because we have seen it many, many times in our lifetime. So we will have fluid motion in the z direction and y direction, but there is no motion based on what we see on the free surface. There is no motion in the x direction. Before moving forward, there is one thing we need to make sure we understand. The idea of the hydrostatic pressure was that if you keep the depth constant, and that's for the fluid at rest, right? We will have constant pressure lines. So as long as your depth is the same, your pressure on this line is going to be the same, which means your free surface pressure is constant, okay? But when you add motion to this, what's going to happen is that free surface pressure is going to remain constant, but the real depth here is going to be different, right? Because this free surface has moved a little bit. So the constant pressure lines or isobaric line are going to tilt as well. Okay? There is an important difference between a fluid at rest and a rigid body motion of a fluid. Right? Your constant pressure lines are going to be tilted, and they are going to be parallel to the free surface. So one of the goals here is to find the slope of this line, the slope of constant pressure line. But how can we find that? Let's come to these equations. These equations here, the idea was there is no motion in the x direction. So there won't be any acceleration in the x direction as well. And we only are going to have motion in the y direction and the z direction. We will also have the weight force that is being applied in the z direction. So for linear motion, these two are going to be our main equations. But how can we formulate the total changes in pressure, or dP? If you go back to your mathematics, the total changes in pressure can be equal to the partial changes in pressure in the y direction multiplied by a small distance in the y direction plus the partial changes in the z direction, dz. What does this mean? Let's say you are dealing with a small element of this fluid. It has these dimensions, dy, dz, dy. We want to find the pressure change between these 2 points. It is going to be equal to changes in this direction multiplied by this distance, or the other one, these two, and changes in this direction, changes of pressure in this direction, that's one, multiplied by this distance. Okay, just a reminder from your mathematics. Okay, so we have these partials though. We have an equation for this partial, the changes in pressure in each direction. So let's plug those in. Total changes in pressure between 2 points in a fluid is going to be equal to rho az, rho ay dy negative plus rho g minus az dz. Okay, and again, the goal here is to find the slope of this constant pressure line, right? You want to find this, because if you have the slope, you can essentially have everything. And we're going to see that in examples. So we want to apply this equation, this general equation, to the free surface or any of the constant pressure lines. What does constant pressure mean for this equation, constant pressure line? What does constant pressure mean for changes in pressure? It means that changes in pressure is going to be 0, right? So that equation, negative rho ay dy plus rho g minus az dz is going to be equal to 0 on the free surface. So if the 2 points you are analyzing, you're looking at, are on a constant pressure surface. If one of the points was here and the other one was here, then this wouldn't have held true. Okay, they have to be on the same constant pressure surface. Okay, And these 2 points are essentially very close to each other because we are dealing with derivatives. Okay, so let's move things around. You are going to get, eventually, if you play with this equation, move dz to the other side, then dy to the denominator of dz, move this to this side. This is what you're going to get, ay divided by g minus az. That's actually both of these have a negative sign. That was my mistake. Okay, so you will eventually end up with this equation. This is the slope of a constant pressure line during the linear motion or linear rigid body motion of a fluid. Let me just put in the parentheses here. Rigid body. Is there any questions so far? No? Okay. So let's see how we can use this equation or this analysis in an example. No, I forgot. There is also a negative sign here. Don't forget the negative. So it is negative ay divided by g plus az. Okay. Let's solve an example. So we are looking at this is a cross section of a tank of an experimental vehicle. The rectangular tank is vented to the atmosphere. So we're going to have a vent here. And there is some liquid, some fuel inside the vent, which means that whatever we have, this is going to be the free surface. And the pressure here is going to be atmospheric pressure, which in terms of gauge pressure, the atmospheric pressure is 0, right? In terms of gauge pressure. Okay. The specific gravity of the fuel inside the tank is 0.65. We have a pressure transducer here. That is half a feet deep inside this liquid. And the tank is subjected to a constant linear acceleration, ay. So ay is constant and linear. Just a constant value. We want to determine an expression that relates ay and the pressure at the transducer. Find the relation between pressure here. Let's call it pressure at TR, transducer, and your acceleration. And we are also asked to find the maximum acceleration that can occur before the fuel level drops below the transducer. So the idea was, if you are in a linear motion, the free surface is going to tilt this way. And as you increase the acceleration, this angle is going to be more and more. We want to find the maximum acceleration at which this free surface will drop below the pressure transducer. What does it mean? It essentially means that we won't be able to measure the pressure inside the tank anymore for that field. You won't be able to measure the field pressure because transducer doesn't have any contact with the field inside. Okay, so what is the equation we have? The main equation, dz dy is equals to negative ay divided by az plus g. Here az we are told is 0, so dz dy is going to be negative ay over g. Okay, what is the pressure? How can we measure the pressure at this transducer? That is the main question, right? How can we measure the pressure at this transducer? If this wasn't moving, then the pressure at the transducer would have been gamma g h, right? Which is here half a feet, right? But since we are moving, we will have not gamma g, rho g, or just gamma. But since we have the transducer, your pressure is going to be, the pressure that transducer is reading is going to be smaller. Okay, but how smaller is that pressure at that transducer, at the transducer? Let's say it is not, it is still above this. Okay, so the free surface doesn't look like this anymore because of this motion. It is like this, and this is your original free surface. So if you were at the original free surface, your pressure here would have been gamma multiplied by 0.5. The question I have is, what is the pressure with the new gamma, with the new free surface? It is essentially going to be the same idea. The only difference here is that your H is going to be different. So it's going to be gamma multiplied by 0.5 minus, whatever, let's call this Z1, minus this Z1. Okay, well, how can we find this Z1? If you start your coordinate system here, you essentially have the formula for this line, right? That is going to be your slope of that function, and Z is going to be equals to A multiplied by Y. This is the slope, right? dz dy. So at any location, since we have the slope of this line, if we have the Y, this distance, we should be able to find Z. That's the idea, right? That's from your mathematics. But do we have the Y? Yes, it is given to us. It is 0.75. So your Z, or Z1, is going to be equal to negative AY divided by G, which is the slope of the free surface, multiplied by 0.75. Is this clear? We essentially have to find the new height. That's it. And that's why the slope of that line was important. Okay, so that is going to be the pressure your transducer feels. But we want to find the maximum acceleration. that is going to cause the water level to drop below the transducer. So we essentially are looking at a value at which the free surface is on the transducer. Whatever the value higher than that, whatever value we get higher than that is going to be causing the water level to drop below the transducer, okay? How can we find that based on this equation? We want to find the value, the maximum acceleration we can have before the water level drops below the transducer. So we have to find that specific value at which the water level is at transducer, right? So the free surface is like this at the transducer. So what will be the pressure? What will be the pressure transducer reads when it is actually at the free surface? It will be reading the free surface pressure, right? Because the free surface is there. Does this make sense? Okay, so what is that pressure? What is the free surface pressure? Anyone? Your pressure is going to increase as you increase the height, right? So free surface, what is the height at free surface? We measure the height based on the distance from the free surface. So what is the distance of free surface from free surface? 0. What it means for pressure? Pressure is going to be 0 as well. So atmosphere. So to find that maximum acceleration, we only have to put pressure equal to 0. So we're gonna get gamma minus 0.75 AY divided by G equals to 0. You have the gamma, that's gamma of fuel, which is going to be, we have the specific gravity of fuel, so just have to multiply this value by the gamma of water to find the gamma of fuel, right? We have the gravitational acceleration. We will be able to find this maximum value, AY of max. Okay. Is there any questions? So, what if our container is rotating, not just moving linearly, it's rotating around its center with an angular velocity omega? Let's say you have this container of fluid again. This is your original free surface, and it is rotating around itself, gamma, with a known angular velocity, gamma. What do you think will happen to the free surface? You have seen this before. Like, let's say you want to drink a cup of coffee. It's too cold. Or you want to like solve some sugar in it, right? Use a spoon to stir the coffee. Yeah. So what's going to happen to that free surface when you're stirring coffee? It's the same thing. What's going to happen to the open surface of the cup? And it is going to look like this, right? Okay. Well, how can we analyze this problem? And this is the rotating container. Let's call it rotating container. It's essentially the same thing as before. we are going to go back to the main hydrostatic equation. Main equation for pressure gradient, if you will. And try to analyze, start the analysis from here. The main problem here, if you will, is that we are dealing with a cylindrical system. It is not a Cartesian system anymore. So we have to employ the analysis from a cylindrical coordinate system standpoint. Okay. So we are not dealing with x, y, and z anymore. We are dealing with r, theta, and z. Okay. So our pressure gradient in a cylindrical system is going to look like this. Partial pi, partial r, plus 1 over r, partial pi, partial theta, and it is ER, E theta, and partial pi, partial p, partial z, EZ. So these are the unit vectors in R, E of R, E of theta, E of z are the unit vectors in R, theta, and z direction, which are essentially the same thing as I, J, and K in the Cartesian coordinate system. Okay, but what are the accelerations? We are going to have, because of this rotating motion, we are going to have a radial acceleration, if you will, which is going to be r omega squared negative, and is in the r direction. A theta is going to be 0. A z is also going to be 0. So the only terminal acceleration present here is going to be the radial acceleration that is there because of the presence of this angular velocity. Okay, so if you want to write this equation, the hydrostatic equation, the main equation we are dealing with, it is not hydrostatic anymore, but the main equation we are dealing with, we're going to get partial pi, partial r is going to be r omega squared. The gradient is equal to this. Okay. I forgot the rho r omega squared. And partial pi, partial theta is going to be equal to 0. Yeah. And partial pi, partial p, I don't know what I call it. Partial p, partial z is going to be equal to negative gamma, which is there because of the weight of the fluid. Again, here in this problem, we want to find the slope of the constant pressure lines or the free surface. We want to find this slope, constant pressure line or free surface. This is the goal again. So we have to employ the same analysis we did. The changes of pressure is going to be equal to dP is going to be equal to changes in R multiplied by the small distance in the R direction plus changes in Z multiplied by the small distance in the Z direction. If you apply those values in, play with it a little bit, and then deal with it at applied actually to a constant pressure line, which means that dP has to be 0. We are going to be able to find the slope of this constant pressure line, which is going to be R omega 2 divided by G. Any questions so far? We can actually go a little further this time. We could have done this before as well, but we don't need to. We can take the integral here with respect to R, which is going to be Z equals to R squared omega squared over 2G plus a constant value. And a constant value is a height for which you know we are looking at the free surface. This is a free surface equation. Okay. Let's say you know the height at this location, and you know the radius here, you will be able to determine this constant C. Then we can also, based on whatever we have had, we can also determine pressure of this constant pressure line as a function of R and Z, rho omega squared over 2 minus gamma Z plus another constant. We can determine this constant for a given pressure at a given location. So to be able to determine this constant, we have to have pressure, let's call it P1 at R1 and Z1. Okay, so let's solve an example from this part. We can, this is the example, this is what the example is about. This type of system, a rotating fluid in a container, right, can be used to measure the angular velocity of a shaft. And it is being used, actually. It is used to determine the angular velocity of the shaft. And in this example, we are going to focus on that. So it is telling us that we will be able, in this type of system, which is connected to a shaft with an unknown angular velocity, omega. We want to find the angular velocity. That is the eventual goal. But it says if you have, let's say this is your original non-rotating height of the free surface. If you have a device that can measure this height, then we will be able to determine the angular velocity, right? But the first thing we need to find the equation that relates to angular velocity to h, to that height, or any of the heights. But how are these two heights related to each other? Can come back to this equation. The constant of this equation is going to be, let's call it H naught. This is H naught. So at R equals to 0, let's actually do that. Let's say we have been able to measure this height, okay? Through, like, we have devices that can do that. If you have passed your lab courses, have you passed any of your lab courses? Yes? Okay, if you have passed your lab courses, and if you have had a bending experiment, we have these measurement devices. There's this thing, if you bend the system, this will move with the bended rod, and you can measure this distance, this deflection. It's essentially the same idea. I don't know if you have done any bending tests, but the point is, it is easy to measure this height. Okay. So for this equation, we want to determine this height based on the values we already have. At R0, your Z is H0, right? Or H minus H0. So your C1 is going to be equal to H minus H0. So your Z is always going to be equal to R squared omega squared over 2G plus H plus H0. But we are interested in this distance, not the distance from the free surface, the distance from this bottom, which is going to be H, right? This H itself is equals to capital H minus Z, right? This is Z. This whole thing is capital H. If you plug that in, you can find the height from the bottom of the container to be R squared omega squared over 2G plus H0. Okay, so we have the equation of the free surface line, right? We have the constant, we have determined the constant, and we want to find the angular velocity. What do you think we should do? The only information we have at this point that relates any type of height to angular velocity is that equation, right? H equals to R squared omega squared over 2G plus H. But that doesn't really help us when it comes to determining the angular velocity. What do you think we should do? Just think about it for a couple of seconds. Why do you may ask, why doesn't this equation help us? Because we have too many independent variables that are changing. R changes from 0 to R. H is changing from 0 to H, right? And omega, we don't know. So there are too many unknowns here. We have to reduce these unknowns. And the goal here is to reduce the unknowns. How should we do that? How should we do this? One thing we can, you want to say something? You moved your hand, I thought. I got excited. One thing we can think of is find what is the value, what is the parameter that is not changing between the 2 points. One, the initial point when there is no rotation, and then a final point when we have already applied the rotation and the fluid is already stable. So it is all of the fluid particles are moving at omega velocity, right? The inertia and all of those, the transient parts have faded. What is the thing that is going to remain exactly the same between the initial condition and the final condition? It is the volume, right? If you don't have any spillage out of the container, which is the assumption we are making, your initial volume is going to be equal to your final volume. How can we find the initial volume? Let's call this radius capital R. The initial volume is going to be pi R squared multiplied by H, right? It's a circular container, so, but how can we calculate this volume? That is going to be the tricky part. To be able to calculate this volume, we essentially have to come back to mathematics. We have to take a very small element of the surface and calculate the volume for this thing. Okay. What is the volume of this? And that is going to be dV. And if we can calculate the volume of this, then we can integrate from 0 to capital R. Will give you the total, give us the total volume as a function of H and R. What is the volume of this? This surface area, okay, multiplied by this length, which is going to be 2 pi R or 2 pi dr H. This surface area is going to be 2 pi dr and 2 pi RH dH. Do we understand where this volume, this small elemental volume, come from, or no? That's the volume of this very small element, right? So you have to calculate this surface area multiplied by this length. It will give you that volume. Okay, so 2 pi RH dH. So your initial volume, total volume, is going to be equal to integral of this small elemental volume, which is 2 pi R H dH. That's, why did I do this? That's dr, I'm sorry. That was my mistake. I did the dr first. Let me actually, I think it may create confusion, so it is not a bad idea to explain this. This a small elemental volume. The radius here is R. Radius here is R plus dr, right? The surface area with R is pi R squared. The surface area with the outer one is pi R plus dr squared, right? And this one, the H here is H. This one is H plus dH. Okay? So we're going to get pi R squared H for the smaller cylinder. This multiplied by H plus dH for the larger cylinder. You just have to subtract these two, and you should get to this dV, in case you were wondering. So we take this integral from 0 to R. Eventually, if you take the integral, you are going to get to this equation. Pi omega squared R to the 4 over 4G plus pi R squared H naught. Final volume, initial volume, they have to be equal. And the only parameter that is unknown here is your omega. Pi, we already know what pi is. R is the radius of the container. H, this is the initial free surface height. H naught is the final free surface height. And we have everything here except for omega, and we will be able to measure omega here. Is there any questions? I know that volume part may be a little confusing, so if you have any questions about that part, let me know. Or if you feel like you need me to repeat that, let me know. Okay. So let's go ahead and solve some example problems. This first example problem is from the monometer part of the chapter. We are going to introduce a new parameter. The problem is called the sensitivity of a monometer, SEN, which is defined as height divided by P of left side of this specific monometer that I'm going to draw minus the pressure of the right side. And this is what it looks like. We have two columns of fluid. We have two free surfaces here, PL, PR. And then the monometer fluid is a different fluid than the two fluids. We have water on both sides, and there is a fluid, a monometer fluid. We can replace the monometer fluid. We have three options. The first option is a kerosene with a specific gravity of 0.82. We have SAE10 oil. This is oil. A specific gravity of 0.87. And we have the normal octane with a specific gravity of 0.71. We want to see which of these monometers fluid are going to give us the highest sensitivity. So which of these is going to give us the highest sensitivity, this SEN? You want to find this maximum here. And we are also told that these areas here, AL and AR, are much larger than the cross-sectional area of these tubes here, which essentially means that and I'm going to tell you what H is. H is much smaller than this H. So let me give you what are the H's. This is H of L. This is a small h of L. This has to be a little higher. This is h of R. This is capital H of R. So these capital H's are much smaller than these small h's. And this height difference is also called just h. So which of these three is going to give us the highest sensitivity? How should we approach this problem? We essentially have to find the pressure differential between PL and PR. Let's do that. PR we are dealing with hydrostatic pressures again. So PR is, we are going to base everything here at this level. Okay, so let's find the P at this location. It's going to give us the same pressure for both sides. PR plus HR, gamma of water, H of R plus, what else do we have here? Gamma of water, a small hr. Okay. And also, what else do we have to include? So one column, at this point, we have the pressure here. Do we need to include the pressure at this point, at this height as well or not? The answer is no. Why? Because the two sides of this tube contain the same fluid. So the pressure here is equal to pressure here. We don't need to go down to this level, right? Okay. Then, so essentially, we have the pressure at this point. Let's call it point R1, and let's call it point 1. We have the pressure at these 2 points, and they are equal to each other. This is the pressure. Then we want to move to this tube right here. If you have the pressure here, we are going to have the same fluid in this tube, which means that we have the pressure here. So P2. Okay, so we have the pressure at this level. But we want to find an equation that will calculate PL for us. So we have to move to this other column. The surface of the water on this tube is here. So this height is going to be important for us. Are we all following this monometer analysis? Did we miss anything? Again, we want to find the pressure, this pressure difference, PL minus PR, right? To find the pressure difference here, we have to move from this open surface, this free surface, to this one, right? Okay. And at this point, we have found the pressure at this location, right? What we could have done, let's actually do it completely. What we could have done, we want to find the pressure here and then move on to this location, right? So let's add that pressure here. It is going to be H gamma W, right? But then when you come to this part of the fluid, you are moving in this direction. So your pressure is going to reduce minus H gamma W, right? So these two will cancel out. We don't need to include that thing. But then the next step is to move inside this monometer fluid to this location. Again, we are moving upwards in this direction. So you're going to get negative gamma F. Your pressure is going to reduce. This is gamma of fluid, whatever fluid that is, multiplied by HR. And then we are moving on down to this point, which is going to be gamma F plus, we are moving down. So your pressure is going to increase, gamma H and that is HL, right? That is HL, yeah. Gamma F HL. This is HL. That was minus HL. Okay. Which we can simplify these two as well, but we're gonna leave the simplification to the other point. So we have the pressure at this point now. We can move to this other side of fluid. Should give us the same pressure because it's the same fluid. And then we are moving upwards again in the direction of lower pressure. So a negative sign, gamma of water. We are again in water. It is HL plus H, a small HL. This all has to be equal to the pressure on the left-hand side. Yeah. Is this clear? Right? Did you guys follow? It is not a very complex operation, but you just have to make sure that you follow every step. If you are moving down, your pressure is increasing. If you are moving up, your pressure is decreasing, so negative signs, right? And then if you have the same height or the same depth in the same fluid, then the pressure of the two columns have to be equal. So you can play with that around, and eventually this will be the final pressure differential you're going to get. It will be gamma water, H plus H, where H is the height difference between these two free surfaces. Free surface, this is H. And minus plus gamma F H. So H is the height difference between the two free surfaces, and this H, a small h, is the height difference between the two sides of the monometer fluid. But we were told that this H is much, much smaller than this. So we can just take this out. And eventually the pressure differential is going to be gamma of water plus gamma of your fluid, whatever that fluid is, multiplied by H. It has a negative sign though. Sorry. I'm pretty sure if you do the math here, you will get to the negative sign. So we can replace this PR minus PL with this formula we have here in the sensitivity equation. And then just plug the values in. Gamma of any fluid is going to be the specific gravity of that fluid multiplied by gamma of water at 4 degrees centigrade. That was the definition, right? That was the definition of specific gravity, if you recall. If you don't, then you can go back to the notes and find it out. Is there any questions? Was this problem confusing at all? Not confusing. Confusing. So. Where's the confusion? So. Oh, you don't know. Okay, a lot of information. Are we all on the same page as him? It's a lot of information and it is confusing just because it's a lot. Okay, that makes a lot of sense. Okay. So, yeah, I will post the homework on Thursday, so you will have a lot of time to practice. But if you have any specific questions, please ask. If not, then we can move on to the next problem. This next problem is actually going to be a little more confusing, if you will. So stay with me. I don't think we can finish this next problem today. We are going to do the rest of whatever remains of the next problem for the next lecture, but we are going to start a discussion. And this is one part of the chapter that we didn't solve any example problem from. So I just want to make sure that I include a problem. This is, we have this type of gate. So there's this. We have this gate here. This is the gate. On one side, this side, we have water with a free surface, right? The height here is h, and here we have air, the atmospheric A. So this is your gate. The height here is h. The length here is L. And we are told that the hydrostatic pressure on the vertical side creates a counterclockwise moment about the hinge. This is your hinge. And the hydrostatic pressure on the horizontal side creates a clockwise moment about the hinge again. We want to find the net clockwise moment. So sigma m clockwise. This is the question. So we have two main forces here. One force is going to be your vertical force, F of V, and one other force is going to be your horizontal force, F of H, that are going to generate moments. But what is the F of V here? And all of these are hydrostatic forces, so they are essentially a function of your depth, right? F of V can be calculated from the pressure distribution on the bottom. Since on this horizontal plate, the depth of the fluid doesn't change, your pressure is going to be uniform. Okay? Pressure is not going to increase or decrease, and it's going to be equal to gamma of water multiplied by this H. So at this depth, your pressure is going to be gamma H, which is going to remain constant throughout this horizontal plate. So gamma H. How can we calculate this F of V, the vertical force? Gamma H multiplied by your area. Area here is the cross-sectional area on which this force is being applied, which is going to be your this length multiplied by the length in this direction, which we can just call B. Let me see. Yeah, we can just call B. So your area is going to be L multiplied by B, just a constant value, whatever. Okay. What can we say about the horizontal force? Horizontal force, we have the hydrostatic pressure here. But the hydrostatic pressure, your pressure is increasing from a value 0 to a value gamma H. So we're going to get gamma H here and 0 at the top. If you recall, we can find this hydrostatic force from the pressure prism analysis we did in the previous lecture. If you do the pressure prism analysis, you are essentially have to find a volume that this distribution makes, right? So it is going to be this area multiplied by the depth of this gate. The depth is going to be B. This area is going to be 1/2 gamma H multiplied by H, right? So 1/2 gamma H multiplied by H multiplied by B. Okay. Is there any questions here? So we have the forces that are going to create the moment, right? This uniform force passes through, the vertical force passes through which location? We already know that this force passes through the center of pressure, or yeah, center of pressure, which we talked about at the beginning of this lecture. And we have to find that location. But what can we say about this vertical force? This vertical force is a uniform force. And what is the location that this force passes through? Just think about it. We have a uniform distribution of force. We want to find the location that the resultant force passes through. Whenever you didn't know or you were confused about this, come back to the analysis you did in your solids, right? If you have a uniform distributed force, where is the maximum deflection? In the center, right? This is a uniform force. So the resultant force is essentially passing through the center, right? So the moment this force is passing through the center, which is going to be L/2, and the moment it is creating is going to be L/2. So let's call it M of vertical, right? Or counterclockwise, or clockwise actually. Clockwise moment is going to be gamma H LB multiplied by L/2. What about the horizontal force? The horizontal force passes through the center of pressure, and we only need to know this length, right? This location. If you go back to the equations, this location, the y of we are looking, we only need to find the y of this location was equals to the centroid's location, which is the middle point here in this problem, multiplied by I of xc, the moment of the second moment of area, or moment of inertia, divided by y of c multiplied by a, the cross-sectional area. Y of c is going to be h/2, right? That's the centroid's location. And this in a rectangular, it will be midpoint, right? A is going to be h multiplied by b. The only thing we really don't know here is I of xc. Does anybody remember what was the moment of inertia of a rectangle? No one? That's a cubed, right? Yeah. BH cubed. Exactly. But you don't need to memorize this. You can just go back to the formulas you have and find this. And eventually, we are going to get this location to be 2h divided by 3. This is the location this horizontal force passes through. Okay. So the moment this creates is going to be this multiplied by 2h divided by 3 divided by 3. This is going to be the counterclockwise moment. This is a negative value based on the definition. Counterclockwise moment is negative, right? This is just a sign of convention. And eventually your sigma m is going to be equal to gamma h lb L over 2 minus this value, 1/2 gamma h multiplied by h multiplied by b multiplied by 2h divided by 3. Okay, so let's stop here, and we're gonna pick the rest of it up. Pick it back up in the next lecture. But in the next lecture, what we are gonna do is we are going to find this height, find the height that is needed to prevent this gate to open. So essentially, this moment has to overcome this moment to prevent the gate to be open. That's it for today. Have a great day. And